Results Results of Bohr theory. Bohr's theory is used to derive the energy of orbit, that is, the stationary states in hydrogen atoms. The results of Bohr's theory for hydrogen atom are summarized here. A. The stationary state for electrons are doubled. N is equal to 1, 2, 3. These integers are known as principal quantum number. B. The radar of the stationary states are R and is equal to n square A0, where A0 is equal to 52.9 picometer. Thus, the radius of the first stationary state, called Bohr radius, is 52.9 picometer. C. The most important property associated with the electrons is the energy of its stationary state. It is given by the expression E1 is equal to minus RH 1 upon n square, where n is equal to 1, 2, 3. RH is the Rydberg constant for hydrogens and its value in joules is 2.18 10 raised to minus 18 joule. The lowest energy state is called the ground state. Energy of the ground 1 upon 1 square state is E1 is equal to minus 2.18 10 raised to minus 18 1 upon 1 square is equal to minus 2.18 10 raised to minus 18 joule. Energy of the stationary states corresponding to n equal to 2 is E2 is equal to minus 2.18 10 raised to minus 18 1 upon 2 square is equal to minus 0.545 10 raised to minus 18 joule. Just think, what does the negative sign of electron energy convey? A free electron at rest is an electron that is at infinitely from the nucleus and does not experience any electrostatic force of attractions towards the nucleus, and therefore it is assigned the energy value of 0. The negative sign means that the energy of the electron in the atom is lower than the energy of a free electron at rest. Mathematically, this corresponds to setting n equal to infinity in the equation so that E infinity is equal to 0. As the electron gets close to the nucleus, n decreases. En becomes large in absolute value and more negative. The stationary states with smaller values of n have large and negative energy. The negative sign corresponds to attractive force between the electron and nucleus. Do you know? The Bohr's theory is applicable to hydrogen atoms and hydrogen-like species which contain only one extra nuclear electron. Problem 4.6. How many electrons are present in 2,1H and 2He and He+? Which of these are hydrogen-like species? Solution. Hydrogen-like species contain only one electron, 2H1. Number of proton is equal to 1 number of electron. 2He number of proton is equal to 2 number of electron. He plus number of electron in helium 1 equal to number of electron in helium plus is equal to 2 minus 1 equal to 1. Thus 2, 1H and helium plus are hydrogen-like species. D. Bohr theory can be applied to hydrogen-like species. For example, helium plus, Li2 plus, lithium 2 plus, beryllium 3 plus, and so on. Energy of the stationary states associated with this species are given by En is equal to minus 2.18 10 raised to minus 18 z square upon n square joule, and radar by the expression Rn is equal to 52.9 n square upon z picometer, where z is atomic number. From the above expression, it can be seen that the energy decreases, become more negative, and radius becomes smaller as the value of z increases. E. Velocity of electron can also be calculated from the Bohr's theory. Qualitatively, it is found that the magnetic velocity of an electron increase with increase of z and decrease with increase in the principal quantum number n. Problem 4.7. Calculate the radius and energy associated with the first orbit of helium plus. Solution. Helium plus is a hydrogen-like species having the nuclear charge Z equal to 2 and for the first orbit n is equal to 1. Radius of the first orbit of helium plus is R1 is equal to 52.9 n square upon Z is equal to 52.9 multiplied by 1 square upon 2. Energy of first orbit of helium plus En equal to minus 2.18 10 raised to minus 18 Z square upon n square joule equal to minus 2.18 10 raised to minus 18 2 square upon 1 square is equal to minus 8.72 10 raised to minus 18 joule. 4.6.3 Explanation of the line spectrum of hydrogen using MAHARASHTRA theory. The line emission spectrums figure 4.5 obtained from atomic hydrogen can be explained quantitatively using BOHR'S theory. According to second postulate of BOHR'S theory, radiation is emitted when electron moves from an outer orbit of higher principal quantum number Ni to an inner orbit of lower principal quantum number Nf. The energy difference delta E between the initial and final orbits of the electronic transition corresponds to the energy of the emitted radiation. From the third postulate of Bohr's theory, delta E can be expressed as delta E is equal to EI minus EF. According to the result derived from Bohr's theory, the energy E of an orbit is related to its principal quantum number n by equation 4.6. E is equal to minus RH upon 1n squared. Combining these two equations 4.9 and equation 4.6 we get delta E is equal to minus RH upon n1 square minus RH upon nf square is equal to RH in bracket 1 upon nf square minus 1 upon ni square. Substituting the value of RH in joules, we get delta is equal to 2.18 10 raised to minus 18 1 upon nf square minus 1 upon ni square is joule. This expression can be written in terms of new number of the emitted radiation in the following steps. We know delta E is joule is equal to H joule second multiplied by nu hertz, and by definitions nu bar per centimeter is nu hertz upon c centimeter per second. Combining said equation 4.10 equation 4.1 and equation 4.11 we get nu bar per centimeter is equal to delta E upon H joule multiplied by c per centimeter 1 upon c centimeter per second is equal to 2.18 10 raised to minus 80 upon 6.626 10 raised to minus 34 multiplied by 3 multiplied by 10 raised to 10 1 upon nf square minus 1 upon I square per centimeter. Nu bar is per centimeter 109677 in bracket 1 upon nf square minus 1 upon ni square per centimeter. This appear like the Rydberg equation 4.3 where nf equal to n1 and ni equal to n2. In other words, Bohr theory successfully account for the empirical Rydberg's equations for the line emission spectrums of hydrogens, and the Rydberg equations n1 and nf are integers. Bohr's theory assigned physical meaning to them as principal quantum number corresponding to the concentric orbits. The integer in Rydberg equation stands for the final orbit nf, of electronic transition in N1 for initial orbits. The emission line comprising 5 series thus are a result of electronic transition from the excited hydrogen atom. The Lyman series is the result of moving of electron excited to the higher orbits of N2 is equal to Ni equal to 2, 3, 4, etc. to lower orbit of N1 equal to Nf equal to 1. The Balmer series result from electron from N2 equal to Ni equal to 3, 4 to the lower orbit of N1 equal to Nf equal to 2, so on and so forth. The electronic transition giving rise to different emission line series of atomic hydrogen are shown in figure 4.6. Wavelength Lyman series, Balmer series, Paschen series, Bragg series, Bevan series. Ionization enthalpy of hydrogen is 1312 kJ per mole. Electronic transition in hydrogen spectrum. Problem 4.8. What is the wavelength of the photon emitted during the transition from the orbit of n equal to 5 to that of n equal to 2 in hydrogen atom? Solution. The wave number of transition given by Rydberg expression. Nu bar is equal to 109677 1 upon n1 square upon minus 1 upon n2 square per centimeter. Here n1 is equal to 2 and n2 is equal to 5. Nu bar is equal to 109677 upon 1 2 square minus 1 upon 5 square is equal to 109677 and bracket 1 upon 4 minus 1 upon 25. 109677 multiplied by 21 upon 100 is 223032.17 per centimeter. Lambda is 1 upon 23032 minus 17. Lambda is equal to 1 upon nu bar equal to 4.34 10 raised to minus 5 centimeter. Wavelength of photons. Lambda is equal to 4.34 10 raised to minus 5 centimeter equal to 4.34 10 raised to minus 5 multiplied by 10 raised to 7 nanometer is equal to 434 nanometer. 46.4 Limitation of Bohr model. First, Bohr's atomic model failed to account for finer detail of hydrogen atom spectrum observed in sophisticated spectroscopes experiment. Second, Bohr model was unable to explain the spectrum of atom other than hydrogen. Third, Bohr theory could not explain the splitting of spectral line in the presence of magnetic fields, Zeeman electric fields type effect. Fourth, Bohr's theory failed to explain the ability of atom to form molecule by chemical bonds. It was therefore thought that a better theory was needed to explain. It was therefore thought that a better theory was needed to explain salient feature of atomic structures. 46.5 Reason for failure of Bohr's models. With limitation of Bohr model for hydrogen atoms, becoming transparent attempts were made to develop a better and general model for atom. This was possible because two important developments took place after the Bohr model was postulated. This development were first, de Broglie proposal of dual behavior of matters, and second, Heisenberg uncertainty principles. In Bohr's model, an electron is regarded as a charged particle moving in well-defined circular orbits above the nucleus. In contrast to this, de Broglie proposed in 1924 that matter should exhibit a dual behavior, that is, both particle and wave-like property. This means that electron should have momentum p, a property of particle, as well as wavelength lambda, a property of wave. He gave the following relation between lambda and p of material particle. Lambda is equal to h upon mv is equal to h upon p. De Broglie production was confirmed by a diffraction experiment, a wave property. Internet, my friend. collect information about structure of atoms. In the year 1927, Werner Heisenberg stated the uncertainty principle. It is impossible to determine simultaneously the exact position and exact moment or velocity of an electron. In other words, the position and moment of an electron cannot be determined with the same certainty. If the certainty of determination of one property of the two is high, it means that the uncertainty of its determination is low. In that case, the uncertainty of determinations of the other property is very high. Mathematically, Heisenberg's uncertainty principle is expressed as delta x multiplied by delta px greater than or equal to h upon p 4 pi. Delta x multiplied by delta vx greater than or equal to h upon 4 pi. Delta x multiplied by delta vx greater than or equal to h upon 4 pi. Here delta x is the uncertainty in position and delta px or delta vx is the uncertainty moment. A further implications of uncertainty principle is that for electron having certain energy, one can only determine its probability at a particular point x around the nucleus. BOHR'S model describes concentric orbit as well define path of the electron rotating about the nucleus and calculate energy of electron occupying these orbits. Bohr's model assumed that both position and momentum of the electron in hydrogen atom are known exactly at the same time, which is ruled out by the Heisenberg uncertainty principle. Hence, no attempt was made to extend the Bohr model to other atoms. A different approach to atomic model, which would account for particle duality of matter and would be consistent with Heisenberg's uncertainty principle, was required. This became possible with the development of quantum mechanics.